elastic collisions and inelastic collisions. Okay, and you're going to have to know the difference between those two. Okay, that'll be something that we need to know. But elastic collisions mean things are separate after the collision, post-collision. And inelastic collision means that things stick together post-collision. So this introduction we're giving with elastic collisions and inelastic collisions. When we see collisions that are elastic, they're going to collide and bounce apart. In what we consider a perfectly elastic collision, we see a conservation of kinetic energy. Okay, kinetic energy is conserved. If the collision is considered perfectly elastic, kinetic energy is conserved. So what does that mean? What's the term conservation mean in terms of our energy? What'd you say? It's not losing it, it's not gaining it, right? Conservation means it's not created or destroyed. So that means within the collision, all of our energy is transferred. Now, we saw with energy systems, sometimes we have work and energy that is not conserved, right? Where does energy dissipate to in real life systems? Friction, right? Air resistance, things like that can help or can keep our energy systems from being conserved. And that could be the case here in momentum as well, right? We have collisions, or we might have collisions, especially with AP style questions, where kinetic energy is not conserved. We're really going to focus our efforts on the perfect physics world types of collisions, right? And then when we come across those problems, we'll explore what that might mean, how we can deal with systems that are not conserved. But for most collisions, we see that a kinetic energy is completely conserved. In inelastic collisions, objects stick together, and so we don't have a perfect transfer of energy. We have kind of a split of energy, and then it carries on as one continuous system. Okay, so that's kind of our introduction here, but let's talk about momentum. Momentum is mass times velocity. Mass times velocity. Now, what's our delta mean right here? Change in, right? Change in, or final minus initial. But the way we write out our equation can really just be P equals mv, right? We know that if we add a delta to the front, we're going to take final minus initial, right? And the mass would not be changing, so we would have to talk about the change in velocity. But I don't think it's necessary to put that into the equation every single time. So if we want to find the change in, we could add that delta onto there, but we don't need it for basic systems. Okay, momentum is a vector quantity, which means it has to have what two things? Direction and magnitude, right? It has to have direction and magnitude. Direction can be positive, negative, or it could be the cardinal directions. Okay, momentum is very simply in the direction that our object is moving. Okay, if our object is moving east, our momentum is to the east. Now, let's say that our object is moving east, collides with something, and is now moving west. Our change in momentum there would be negative, right? We would have a change in momentum that caused a direction change. So we'll look at that a little bit later, but momentum is very simply in the direction of the motion. The unit for momentum, I wish was cooler or smaller, but it's not, right? It's just literally the mass unit times the velocity unit, kilogram meters per second. Okay, it's long and cumbersome, but that's what it is, right? It doesn't get an abbreviated unit like newtons or something like that. So that's just the unit for momentum. Okay, a large truck and small car are moving at the same speed. Which is more difficult to slow down or to stop? If I'm trying to stop this thing, but if I have a large truck and a small car moving at the same speed, which is more difficult to slow down? The truck, right? And what's that contributing factor? The mass, right? They're already moving at the same velocity, so the truck is harder to slow down. Which has greater momentum? The truck, right? Because mass times velocity, and if their velocities are the same, mass contributes to that momentum as well, right? We think about, you can really visualize momentum when we're talking about, small rock, big boulder, right? One is much harder to get started and much harder to slow down. One is much less difficult to start and slow down, right? More momentum can be mass or velocity, right? So both of those things are contributing factors. All right, so let's just try one here. Do you have your calculators out? If the runner has a mass of 65 kilograms, what's the momentum? Right, that's literally as easy as it seems. Momentum is just mass times velocity. That's all we need to do, right? I wish I could tell you why momentum is labeled with a lowercase p, but I don't know. M's are used up for everything else, I think, so that's what it is. Lowercase p. What's uppercase p? Power. Yep, power. Lowercase p is momentum. So m times velocity. Okay, so mass times velocity, 65 times 3.21, gives me 208.65 kilogram meters per second. And what do I need to include here? The direction. So I'm just going to go ahead and tack west onto the end, right? The general rule for us is if we're given a cardinal direction, we want to include a cardinal direction. Okay, if we're not, then we can go positive, negative. Any questions here? Easy peasy so far, right? Just plug it in. Okay. A boulder is found to have a momentum of 4,115 east. If the velocity is 16.4, what's the mass, right? So we're just working the same type of problem in the other direction. Momentum is 4,015 equals mass times velocity. Gives me a mass somewhere around 245 kilograms, 244.8. Did I plug something in wrong? Is that what you had? Okay. All right, so we're somewhere around there. So momentum itself, very simple, right? But it contributes to bigger issues, okay? All right. This one says an object is dropped from a height of 8.8 meters above the floor. What is the momentum after 1.2 seconds? Okay, what is the momentum after 1.2 seconds? So we've got the mass, but we don't have the velocity, right? And if I want momentum, I need to take mass times velocity. So I've got my time, I've got my y final, right? I'm able to just use kinematics to solve for velocity. Okay, are we agreeing there? Okay, and if I'm going to look at my kinematics equations, I'll probably choose, I guess I'll probably choose the second one. I could really use second or third. Yeah? I think I could use the second or the third one. I'm going to use the third. VF squared equals 0 squared plus 2a negative 8.8, right? Why am I making my 8.8 negative? It's going downward. It's landing below where it started. So 8.8 times 9.8 times 2 square root of that. And I get a velocity of about negative 13.13. Is that similar to what you had? It probably came out positive, right? It comes out of the equation as plus or minus, but I know it's going downward, so I'm going to keep the negative. And then to find momentum, I would take mass times velocity. And I get about 39.4 kilogram meters per second. Did I do something wrong there? I'm getting funny looks. Do I have a number that's different than yours? So based on the problem you guys have on your sheet, it's only the time, not the height. Okay, so now let's say velocity final is 0 plus a times 1.2. And I get negative 11.76. Okay, there we go. Sorry about that. Momentum equals mass times 11.76. And I get about negative 35.3 kilograms meters per second.
Why does it give different answers?
Yeah, okay. I think that I made this problem up and didn't double check. And that's why I took away the height from your problem.
Oh, okay.
You know what I'm saying? I put in a height and I put in a time, and I wasn't thinking about the fact that you could use either system to solve for it. So this was just my mistake. So I think that's why I took the height off yours, and I just didn't remember to take it off mine. Yeah.
Do you care if we use negative 10 or 9?
I don't care. I kind of forgot that we normally use negative 10. I'm not in my school habit yet, you know. But no, I don't care. So that would maybe give you something a little bit different. Yeah. That. Okay, perfect. No, that's fine. Okay, wow. Or net force is equal to MA. So we're going to ignore this, and I'm just going to walk it through. Okay, so we're going to walk from Newton's second law. Net force is equal to mass times acceleration. Acceleration is the same as change in velocity over change in time times mass equals the net force. You don't have to write all of this down. You just kind of watch if you want. Okay? Mass times velocity looks like what? Momentum. So now we can say the net force is equal to momentum divided by time. Okay, we kind of wiggled our way through kind of a derivation here of equations to go from Newton's second law, which is this one. Worked our way through what is acceleration really, right? It's a change in velocity over a change in time. And then I know that this looks like momentum. So essentially, my net force can be equal to the change in momentum over change in time. Okay, that's one that probably could go on your equation sheet. I'm not sure if AP uses it or not, but you're welcome to have that on there. Yeah, it does have it. You see on your AP sheet, it's right underneath there. Net force equals delta P over delta T, and it kind of works it out. It gives you all versions of that. Okay, so that's a way we can find out how much force was required to change the momentum. How much force was required. All right, so what force is required to stop a 488 kilogram wagon moving at a velocity of 52 meters per second north in 2.3 seconds? So what type of a force is probably being applied here?
Gravity.
If we're going to pull it to a stop,
Friction.
it could be friction, right? It could be just an applied brake, right? It could be both of those things. It doesn't really matter, right? We just know that the sum of these forces is causing our object to stop. Okay, so if we set up our equation to say force, the net force that's going to put this to a stop is equal to the change in momentum. What's the final momentum of my system? 0, right? Because I'm going to come to a stop. So 0 minus, my original momentum is 488 times 52 over my time. Okay, do you see how we got that all plugged in one? This would be like final momentum minus initial momentum. Right? Our final momentum was 0 because my velocity was 0. So then we're just going to plug in. 488 times 52 divided by 2.3 gives me a force of negative 11,033 newtons. And why is my force negative here? Right, it's opposing my motion, right? I'm moving north, so the force that's being applied has to be in the opposite direction, right, to the south. So that's why. That's why plugging in that 0 here was important here, because it gives us the right direction for our force.
Yeah, I know they're really dirty.
4.71 seconds. For some reason, I thought that was different than, oh, okay, now we're good. I'm sure it's only different from this answer because we used 10 instead of 9.8 for gravity. Everyone feeling okay about that? Okay, the time it takes for that change to happen. So this one happened relatively slowly because that force being applied is not very big. All right, so it's kind of a slow change there. This next thing is just a kind of a definition change or like a name change, but something called impulse is essentially just the change in momentum. So we have a name for momentum, but the change in momentum is actually called the impulse. And we know a couple different ways to solve for change in momentum. We know how to solve for change in momentum with force times time and mass times velocity. So when two things are set equal to the same thing, you can set them equal to each other. Right? That's all that this is showing. So you're welcome to write this equation down if you'd like. You really already have the other two. Okay? But impulse is just kind of a name change, but it means the change in momentum. Okay? So when we look at a collision or something that happens, the impulse is applied to both objects, right? The momentum change is the same for each object. Sorry, do you have what you need there? All right. What force is needed to bring a 75 kilogram object traveling 44 meters per second north to a stop in 2.1 seconds? 2.1 seconds. So, we're looking for force. We have mass. We have initial velocity, final velocity, and time. So we could use that equation we just looked at. Force delta T equals M delta V. You could also do it in two steps if you wanted to, right? Solve for momentum and then go through and solve for force. But if you're able to do it in one step, that's my preference. Right? Force times 2.1 equals mass times change in velocity. So 75 times negative 44 divided by 2.1 gives me negative 1550.5 newtons. Right? I was traveling north, so my object is coming, or my force is opposing that motion. Right? If I was traveling south, I would make sure that my force being applied here would be in the positive direction. Okay, so just kind of something to look at there. But I will tell you that a lot of questions with AP ask for the magnitude of the force. And what would that mean? If I just ask for the magnitude of the force, I don't have to include the direction, right? So a lot of times with AP, you'll work the question and be like, oh, mine's negative. But there's no negative choices, right? If it's asking for the magnitude, you don't have to include that direction. So that's just something I want you to keep in mind and keep working with that verbiage, okay? Blah, blah, blah. All right, let's get to collisions. We did a bunch of predictions earlier with collisions, and I think we have an idea of how collisions interact, what they look like. But here is our big equation. In a collision, and specifically this is the equation for an elastic collision. Okay, this is the equation for an elastic collision. And we said that in an elastic collision, momentum is conserved. So all of the momentum before is going to equal all of the momentum after. And so here is our big equation showing that. Momentum of object 1 plus the momentum of object 2 is equal to the momentum of object 1 after and momentum of object 2 after. So here's how we know it's post-collision. This little symbol right here, do you recognize that? Do you know what that's called? It's called a prime. Okay, so we call this variable right here V1 prime. And the prime tells us that it is post-collision, right? It's after the collision takes place. Okay, so the 1 and the 2 tell us object number 1 and object number 2. But the prime tells us that it is the post-collision velocity, right, after there. Do we have that equation on our equation sheet? It needs to probably go on your big equation sheet. Okay, we want it on there. All right. Oh. I don't know what's different about yours. I think I have the equation. It just got bumped down. Does yours have the equation written on there or no?
Yeah.
Okay, that's all it is. Okay, find the recoil velocity of a 5-kilogram rifle that shoots a 0.05 kilogram bullet at a speed of 120 meters per second. So we don't really see an actual collision here, do we? But what is the collision? What's the point? Yeah, like the trigger is the collision, right? That's what we're talking about here. That's when things separate. So I want you to start laying out and being really organized through these problems. I'm going to go ahead and lay out each object individually. So I'm going to make the rifle object 1. So M1 is equal to 5. V1, what's the velocity of the rifle before the trigger? 0, right? So this is 0. V1 prime is what we're solving for, right? We don't know the velocity of the gun after the trigger, right? That's what, you know what I mean when I say recoil velocity? What's that mean? Like the kickback, right? It's going to kick back towards you, right? When you fire a gun, bullet goes forward, gun goes backward. So M2 is 0.05. V2, what's our initial object or initial velocity of the bullet? 0. And what about V2 prime? What's that equal to? 120. Okay. So we've got our information, and that's kind of how I would recommend you laying it out, kind of giving it its own entity and own space, but I'm going to let you decide on those. That's fine. And then we're just going to put it into our equation. So M1 times V1 plus M2 times V2 equals M1 V1 prime plus M2 plus V2 prime. Okay, do we see how that goes in, that information goes in our equation? M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Do you see what's the momentum of our system pre-collision?
0.
It's 0, right? Nothing is happening pre-collision. So that means post-collision, these things have to be going in opposite directions, right? For the sum of our post-collision momentum to equal 0, that means the bullet's got to go forward and the gun has to go backward, right? Can we see what's happening there? Because our pre-collision momentum was 0. So this is 5V1 prime plus, let's see, 120 times 0.5 is 6. I'll move that to the other side. So negative 6 equals 5V1 prime. And so my velocity, V1 prime, is equal to negative 1.2 meters per second. Okay, so if we were going to check at what's the momentum of the gun post-collision, this times 5, it would be equal to what's the momentum of the bullet post-collision, right? And that's because our pre-collision momentum was 0. They have to go in opposite directions there. Okay? We feel okay about how that goes in mathematically, right? It's relatively simple math, right? It's just getting things organized in the right spot. Okay, let's try this one. It says 2 pool balls of equal mass collide. The first is moving at a speed of 3.1 meters per second, and the second is at rest. If the collision was perfectly elastic and the first ball came to rest, what is the velocity of the second ball? Do we need to do the math? What is it? It's 3.1, right? Because if the first ball is moving 3.1, the second one is at rest, that means after the collision, the first one comes to a stop, and the second one, the second one is now moving 3.1 meters per second, right? We see a perfect change. It's like the purple and the green that we saw at the very beginning, right? But things that have to be true for that to happen is that we see these keywords, equal mass, and we're really looking for something to say perfectly elastic or to be really explicit about it being an elastic collision, right? Does that make sense? We want to make sure that we try to see those keywords. But that's true. Mathematically, we could prove it, but those are the things that have to be true. It has to have equal mass and it has to be perfectly elastic. And we saw that in that video earlier today.